Hi guys, and welcome to the Daily Maths Challenge number 5. I'm really excited about today's episode, although I have recorded it about 4 times now with my software kind of like going crazy, which is really me just not knowing how to manage it. But anyway, we've got questions basically centered around area today, and I'm really excited about these questions. They're very interesting. Each of them has a different sort of like a few ways that you can approach them. And the last question actually appeared in many different guises throughout my times studying maths at university. So I think it's a really useful result, and I'm really looking forward to this. So let's get started. Okay, so for the first question, let me just get these questions up. So what is the area of the triangle below? So we've got a triangle that has a height of 6 centimeters. Okay, so I'm going to put that there, 6 centimeters, and a base of 3 centimeters. Okay, now this is a special type of triangle. It's what we call a right angle triangle. All that means is that this angle here is a right angle. It's 90 degrees, and actually in this case the height is the same as this length here. So let's think about what the area is. Now the area of this shape, a lot of you might know this already. It's basically the base times the height, and then you divide it by 2. Okay, now for this case we have a base of 3, so we're going to go ahead and write 3 there, and for the height we're going to write 6. Okay, so 3 times 6 over 2, and that's going to be 18 over 2, which is equal to 9 centimeters squared. Okay, now just to remind you about area, the unit is centimeters squared. Now what that means is is what we use to measure the space, the area inside the shape. Okay, just like with distance, if you want to measure this distance here, we would basically divide it into 3 different parts. If there were 3 centimeters there, okay, we would divide it into centimeters and count how many centimeters there are. So 3 centimeters here means that it has a length of 3 centimeters. The way that we write that distance is 3 followed by centimeters. So it's 3 of, and then followed by the symbol that you're counting. So we're counting centimeters. Same thing with area. We're counting centimeters squared. But what does area correspond to? What does centimeter squared correspond to? What does that correspond to? Well, we're counting something clearly, but what is it? Well, unlike length, where we're almost measuring a line. For area, we're measuring the space inside an object. So basically, what we're doing, we're counting how much space, how many of these centimeter squares fit inside our shape here. So if we can cut it and sort of like rearrange it and put it into this shape here, we would be able to fit 9 of these squares into here. So that's a nice result. Now I have another way of doing this actually, a second way. So, and I really like this way of doing it. So if you imagine drawing two triangles now, basically we're drawing a rectangle. So we got 3 centimeters followed by 6 centimeters, right? And actually, we know the area of this rectangle, this whole thing here, is going to be, the formula is 3 times 6, right? The base times the height, and that's going to be 18 centimeters squared, okay? Now, the reason why it works to find the area of a rectangle this way, by timesing the base times the height, is because if you imagine dividing the length into centimeter strips, and also the height into the 3 centimeter, the 6 centimeters that it is composed of, we basically are dividing our shape into 6 lots of 3 centimeters squares. So, 6 lots of centimeter squares. So we have 3 times 6 lots of these squares, but those squares are exactly what we're using to measure how much space, how much area we have inside that shape. So that's why it works to times the length by the height in in a rectangle. That's the same thing as counting how many of those centimeter squares are inside. So obviously if we're looking at just the area of this triangle right now, which is the same triangle as we had earlier, we're sharing that area, all those centimeter squares, evenly between those 2 identical triangles, right? So that's going to be 18 divided by 2, which is giving us back 9 centimeters squared, which is what we got earlier, which is encouraging. Okay, let's go on to the next question. All right, okay, so on to the silver question. So for the silver one, we have that if the shape below has an area of 10 centimeters squared, so this one has an area of 10 centimeters squared, then what is the area of the shape which we obtain from the previous shape by multiplying all the lengths by 2? Okay, so we have this shape done here. So this length here is actually this length, which is here, this length here. and then another one of those lengths, and then this length here is times by 2 to become this length, and this length was we got that one from this length here by timesing this length by 2, and even this one we get it from timesing this length by 2. So basically what we have is all of the lengths have been multiplied by 2. Okay, it's been stretched by 2. So let me draw a copy out over here. Now let me just explain some notation. A lot of you will know this already, just because it should have come up in school maths quite a lot. So whenever you have a line through another line, or like a dash like this, these dashes basically are showing you what lengths are the same, what lengths are the same length. So it's saying that this length is the same as this length, which is the same as this and this and this. So really we have a square followed by an isosceles triangle, right? So a triangle that has two lengths that are the same. Now we want to know, okay, well, if I know that the area is 10 centimeters squared, what happens if we kind of enlarge it by timesing every length by 2? Well, I'm going to show you 2 different ways of doing this, okay? Both are satisfying, but the last one is a bit more sneaky and actually more powerful, because we can generalize it to what happens when you stretch any shape by timesing it every side by 2, okay? So it helps you actually deal with what we call enlargements in maths, where we have a shape and we make it bigger. Really important from everything to maps. Imagine if you want to work out how much floor space you have in this area that you have in your house plan, if you're designing a loft or an extension or anything like that, and you know how many times bigger the lengths are in your actual house compared to what you've written down. Maybe a centimeter wall is 2 meters in this in the actual house. Well, what if you wanted to work out how much paint you needed to paint the wall with, or the floor with? Well, you can work out the area of the what you have in your floor plan, the actual map. So it might be 3 centimeters squared or 10 centimeters squared. That's just like around this big. But actually, and then you can work out how much that would expand to in your bigger floor plan. So yeah, it is really useful to know. And how would we go about it? Well, I'm going to go for more of a visual way. So if you split this in half like that, and this in half, and this in half, what we have, I don't think I've done this well. No, I haven't at all. Okay, so imagine if these lengths is the same as this length, and which is the same as this length and this length. If we split this in half and this in half, and this length in half and this length in half, basically what we have is can you see this shape? Because this length is the same as this length, and this length the same as this length. This square here is actually exactly the same as this one. And how many do we have? We have 1, 2, 3, 4 of those shapes, because this shape is basically twice as big as that one. Similarly, this triangle is this length along and this length along, but that's this length and this length in the doubled version. So we have 1. And actually I'm going to, can I do this? Wait, I haven't thought about this carefully enough. Yeah, I can. I'm going to divide this rectangle in half, and actually this triangle is has the same area as this one and this one as well. Okay, so I've basically got 1, 2, 3, 4 of these triangles, and 1, 2, 3, 4 of these squares. And actually, if one of these guys altogether was 10 centimeters squared in terms of what the area is together, then can you see we can make one more of these, and actually we can make another one by using this square and this triangle, and we have 2 more triangles. They can go with this square and this square, so we can kind of make 4 more copies of this whole shape here. Okay, we can kind of chop the shapes up in this one and rearrange them to make exactly 4 of these older ones. Now that means that we have 4 lots of 10 centimeters squared area in the whole thing, which is 40 centimeters squared, right? If let's remember our centimeters squared. If 10 of them fitted in this one, well, because there are 4 copies of this in this, that means that there are actually going to be 4 lots of these 10 centimeters squared inside the big one, and so we have 40 centimeters squared. Now let me just talk about very quickly about transformation. So if we have a shape, let me just not even talk about that original shape. Let's talk about anything else. So let's just talk about a square, a centimeter square. If we times this centimeter square by time, like if we enlarge it by multiplying all the lengths that occur by 2, then we're going to have 2 centimeters by 2 centimeter square. And so I'm going to roughly divide this like this, and actually can we see we actually have 4 of these centimeters squared inside the new one, right? We can just clearly see that by dividing this 2 centimeters into 2. So each of these is now 1 centimeter, and each of these is now 1 centimeter. So I have 4 of them, okay? Now, the reason why this is really important is if you go back to this picture, imagine if you were looking at 1 of these centimeters squared in the original, right? 1 of these centimeters squared inside the original one. Well, when that gets enlarged, that's going to get bigger, and it's going to get, because all with enlargement, it's not just these lengths that are times by 2 to get the new lengths. It's if you drew any line inside the shape. It's just a fact with enlargements that if you enlarge the boundary lengths by 2 or anything like that, then any line you draw inside the shape is going to get doubled in this case, or you'll times it by whatever scale factor you were timesing the original by to get the new one. So that works with every length, even the lengths that you haven't drawn in. But I can draw this one in, the 1 centimeter squared, and where this corresponds to in the new one is going to be a 2 centimeter by 2 centimeter, which will be 4 centimeters squared, right? Remember, it's going to be enlarged by 2, 4 centimeters squared in size. So imagine, right, the area of this one, it was saying that we had 10 lots of these centimeters squared, and 10 of those 10 centimeters squared in the original, if we cut it up and stuff like that and fit those 10 of them in, they're going to get bigger by 2, which means that in each of the original centimeter squared you can fit into this shape, you now have 10 of these 2 centimeter squared shaped in this, and in each of those 10 of in each of these 10 2 by 2s you can fit 4. So you have 10 of these guys, which means that you're 10 times 4 centimeters squared in the whole of them. Now you might need to pause that and just go over that explanation again, because there's a lot going on. There's a lot of enlargements and there's a lot of things fitting into different things, right? So these 4 centimeters squared fit into the 2 by 2s, and 10 of these fit into that. So there's a lot of things fitting into different shapes. It sounds like some sort of Russian doll from I'm not gonna say from hell, I don't like that expression. Some extreme Russian doll. But anyway, that's what we have. So it's a really nice result. I love it. And so if you enlarge any shape by, let's say, if you times the lengths of any shape by x, then actually the area is going to be times by x squared. Can you see the result in us, the one that we did? We times every length by 2, therefore we times the area by 2 squared by 4, right? That's exactly what we did. So we get, I didn't even write the answer here, we get 40 centimeters squared, and that's it. Okay, so that's the silver question. Let's go on to the bronze. I can't speak. I'm so knackered. I'm doing this at the end of the day. I haven't even left you enough time to do this question. Daily exercise, he says. I've only left you, it's now 7:43, and by the time I edit this, it's definitely going to be probably later than that. So, silly me. Sorry about that. But anyway, goal question. So this is what the goal question reads. If a rectangle is set up so that the lengths of the sides always add up to the same number, what lengths do we choose for the sides so that the area is maximized? So if these lengths here add up to a constant number, so let's say it added up to 4, so we can have either 1 and 3, 2 and 2, we can have 1.5 and 2.5. The possibilities are endless, but what lengths do we choose are A and B to be so that the area is maximized? Now this you might assume that the area is going to be the same for all of them, but let's just quickly see how that's not true. Let's say that you have let's say a 1 and 3 centimeter rectangle. The area is 1 times 3, which is going to be 3 centimeters squared. Now, actually, the area of this square, if both sides are 2 centimeters, now, in this case, in the first one, they add up to 4, and in this case, they also add up to 4. So these are 2 rectangles we could have made with our A and B being constants at 4. Okay, but the area of this one is clearly 4 centimeters squared, which is bigger than that. Now, can you see actually that the square is bigger than the rectangle in this case? Remember, this is still a rectangle, although it's a square. A square is just a special type of rectangle where both sides happen to be the same, but it's still a rectangle. Now, we need to think about what, like, you know, how can we choose both sides so that if they're both adding up to the same constant, let's say that they're both adding up to a number that I'm going to call C. What do we choose A and B to be so that the area is maximized? Well, I want to show you actually something I did on Python. Now, I had to kind of Google again, refresh my memory on how to plot things on Python, so don't get impressed and think that I did this from memory. I laid a foundation for myself with computer science, reading about it, learning how computers worked, which basically took me to read like a textbook this thick, which actually was so enjoyable that it went quickly, and it's easier than you think. Computers are actually quite logical, and if you look at it from the gate level to software level, just looking at each layer, which is what I did. I think the textbook was called Computer Science Illuminated. It was so good. I so recommend it. And I also read another book called But How Do It Know, or How Does It Know? I can't remember how that was phrased. But it was basically explaining how in fact, I think I have it now. I'll show you very quickly. So I really recommend this book. But How Do It Know? This book takes you through how computers work, basically at the circuit level. It was so satisfying. It takes you through memory. It takes you through all those things, and it is easier than you think it is. And the textbook I was talking about, I'm not being sponsored, although maybe in the future I will. I don't know. But right now, I'm not. But this book here, honestly, it's this thick. It takes you through different layers. So we have, at the beginning, we have the information layer, the hardware layer. The hardware layer is to do with the gates and circuits and the transistors and stuff like that. Going to the programming layer, the operating system, application layer, all those things. It is so interesting, and that formed a really good foundation for me to learn coding. And then I learned coding through, I think I was literally baptism by fire. I had to learn it in my when I was at uni doing my projects, coding projects. It was literally a nightmare because I had to do it so quickly. But I did it through a Udemy course. It's like an online Python bootcamp. But I think any online Python course is good. And then just practice things. So I laid a foundation for myself. I can't memorize everything. Doesn't matter. It literally took me a minute to Google and remind myself about how to plot things in Python. And then, you know, I was just on my way. So let me show you how you do this. So can you see I'm actually going on something called Anaconda Navigator. Now, I would recommend installing Anaconda. It is a platform you can use to code Python on. I really recommend it because it gives you access to something called Jupyter Notebooks. And I'll show you exactly how that looks. But basically, it's so nice. It's such a nice platform to code Python on. Someone who was tutoring me at university, I noticed he used it, and I was kind of like made a mental note of it to return to it at a later date, which is exactly what I did. So can you see here, Jupyter Notebook? I'm going to launch that. Let me hide that. It just launches a terminal window, and it's just going to load something when it's ready. Okay, it's done that. Let me just quit something. Okay, gosh, I got a lot of tabs on. That's not bad. So documents, let me go on to, I should really cut this stuff out. I think it's got my personal file system on display. So I'm just never you mind. I'm just going to open a new Python kernel. Okay, so let's see if I can. There we go. Okay, so I've got my my Python kernel open. So I'm going to import a library. I think it's called matplotlib. Hang on. From matplotlib, import. I think I'm going to do this right. pyplot as plt. Is that right? It doesn't look like it's bugging. Thank goodness. Okay, and then I'm going to import numpy as np. So numpy is just like it's a library that's going to help me create like this list that is going up in kind of the same amount each time. I quite like it. It's called something called linspace. But anyway, let me just refresh my memory about what I'm going to do. gosh, I thought I had this. I forgot what I was going to do. So I'm going to visualize. Basically, okay, let's go back to our where is it? Let's go back to this question. So I'm basically going to plot a graph where I'm going to change for a given constant. So for a given a plus b, so let's say a plus b is always 4. What a and b do we choose so that the area is maximized? Well, I'm basically what I'm going to visualize is going to involve me choosing different numbers, different heights, going from 0 to 4, and then we'll see which one will give the biggest area. So I'll plot the area kind of like on a graph, and it should show me like which area gives me the biggest. Sorry, I'm not really doing this properly. Which area will which length will give me the biggest area. Sorry, this is not going well, but I'm going to include this just to show you my humanity. Okay, so let me just remember how I'm going to do this. Okay, so I'm going to first of all define my constant, so c is 4, and then I'm going to look at I'm going to make my x value. So I'm going to make a list of numbers from 0 to 4, which is going to be my different lengths a that I'm going to look at and evaluate at each of those values of a to see what the area is at for each choice of a. So I'm going to use the library np, this function called linspace. Start from 0, I'm going to end at 4, and I'm going to divide this into 100 different points. That should give me a nice smooth graph. And then what am I going to do? Okay, I'm going to do... Okay, this is a kind of fancy way of doing lists. I can't remember exactly what it's called actually, but basically I want to find out the area that we're going to do at each choice of a. So if I have my a... Sorry, I'm not showing you. Oh, sorry. There we go. If I have my a and b, so the area of this is a times b. Right, but more than that, because a plus b is equal to c, which I defined earlier, I defined it as 4 actually. I can say that b is equal to c minus a, so I can express b in terms of a, and then the area, this area, is going to be equal to a times b, so that's going to be a times c take away a. So I'm going to literally jump back onto my Jupyter notebook and show you how that looks. So I have, well, for I times by c take away I, where, so I'm going to do I times by, oh gosh, I times by c take away I, for I in, in x. I think I've done that right. Let me just see if that bugs. Okay, so let's now see how this is going to plot. So now I'm gonna plt plot. I'm gonna plot x and y. Okay, so that should give me the what I did here is y is basically whatever value of a I chose. The x is I'll show you what x looks like. X is like a list of numbers from 0 all the way up, going up in equal steps all the way to 4. And for each of those x's, if you look at my y now, I have, for each of those x's, I have the area of the rectangle where one length is each of these guys, and the other length is obviously that other length, so that our choice here plus the other length is equal to 4, or that constant. Haven't explained that well. You'll probably have to pause that and watch it a few times to kind of try and work out what I was saying. But anyway, I've got the area for each of those choices of my one of my lengths, and that's going to, obviously the area, can you see it's going to increase and decrease, but I want to actually see what's happening, so I'm going to plot it, and let me just delete those. Okay, I'm going to plot plt.plot. I'm using the plot function in the plt library thing, in the plt module, and so x and y, and oh, that's lovely, isn't it? I love it when that happens. So I've plotted x, actually let me label this, so x, plt label, x label. I'm going to label the x as the length of a, and then I'm going to plot the y, I'm going to say that the y label is the area in, that would be centimeters squared, okay? Centimeters squared. Okay, so... Oh, what happened there? You see, I'm learning. I'm still learning. I think we need to do both at the same time. That's what my guess would be. Yeah, there we go. Okay, so we've got this now. So can we see the area is getting as my... sorry, let me just show you this. As my this length increases, it's kind of going to go... Let me just draw a sequence of what it's going to look like. So is that in focus? Yeah, it's in focus now. So I have A and B, so maybe for this choice, and then A gets slightly bigger, but B has to decrease slightly because A plus B has to always equal to 4. And then it gets to a square, and then A gets even bigger, but B's decreasing again. So this is the sort of sequence of length that we have, starting with that smallest A, going bigger and stuff like that. Now let's return to and see what the area is going to be for each of those steps. So for small a, we have a really small area. And actually that makes sense because if we go back to, sorry I'm jumping back and forwards. If we have at the beginning basically at the start, we basically had 0 as a, and then b, greedy b, ate up all of those numbers. It took up the constant 4 completely, right? A plus b has to be 4. It took all of that. And became 4. So actually that has a really small area. It's just 0 actually, the area of nothing. So we expect the area to be 0 at the beginning, which is what it was. And then as it increases, the area gets bigger. And what's interesting is it stops at this middle point. And it's worth noting that that's when the length of A is 2. And because A plus B has to be 4, that actually is the example where we have the square. So that's when the area, the size are 2. And the area is 4 centimeters squared. Now that's actually not obvious that the area changes, is it? I think the first time I thought of this problem a couple of years ago, I wouldn't have thought that the area would be much different, or I didn't know what would maximize or minimize the area, but actually it is when each of the sides are the same. Okay. Now we're going to look at why that works, and I think we can prove it using algebra. So let me just go over to a fresh page. So this is the idea. So if one length is A and one length is B, I can also say that B is C take away A, because A plus B is equal to C, where C is a constant. Remember, keeping C as a constant and looking at all the different values for A and B that we can have for the same C. Now the area is going to be equal to A times B, which is equal to A times, and using this version of B that we have here, A times C take away B, C take away A. Okay, now that's going to be AC take away A squared. I'm going to bring out some more powerful tools for us to use. I'm going to use differentiation. So I'm not going to explain differentiation right now. I don't have time. This is not what, I don't want to go into that video. But I'm basically going to divide this expression by A. That's going to give us the rate of change with respect to A. So the idea is that, oh, here I go, I'm actually going to explain it. So look at, if you think about that sort of curve we had, at the top, the rate of change of the area as A increases is going to be 0, because it's going to be flat. So basically, that's when we differentiate, we're going to get C, because C is a constant, take away 2A, and actually that's going to be 0 at that maximum point. So if I add 2A to both sides, divide by 2, I'm going to get A is C over 2. So A, one of the lengths of the thing, the rectangle, is half of that constant C, which means that because they share C, right, they have to add up to C, B has to be also C over 2, so that's when they're equal. And so that's a really nice way of working out what value of A gives us our maximum point there, which corresponds to the maximum area. And actually we can go further, we can work out what the area is going to be at this point. Well, both of them have a length of C over 2, so C over 2 squared is going to give us C squared over 4. Okay, so actually the area is always going to be C squared over 4, so the area in that case when C was 4, actually that's quite nice, I didn't actually plan for this, this is just a coincidence. 4 squared divided by 4, that's going to give us 4 as well, which so 4 centimeters squared in the case of our example where C was 4.